Hello guys, thanks for coming. Today, we're going to be reviewing a classical paper in a text-to-speech synthesis. The title of the paper is HiFi-GAN Generative Adversarial Networks for Efficient and High-Fidelity Speech Synthesis. Although this paper was published about 2.5 years ago, but since the paper is still, or the technology in the paper is still being widely used in the speech vocoder. So I think it's a good thing for us to just review this paper first, then we can get to the more latest, more recent papers. Okay. What to start? I do want to give you a very quick overview of what is a vocoder. Okay. Okay. Remember, during the Second World War, the Allies are sending telegraphs through oceans. But over that time, the wireless signal are not encrypted. There's no RSA or TSA like we have nowadays. So instead of not making their message secured from being known by the Axis, so they developed something called a code book. So when they want to send some message to the receiver, they first use the code book to, this is called encode. They use the code book to encode the message, while at the receiver end, when they got the message, it's basically something not readable. What they have is that they use the same code book so that they can turn the encoded message through something called a decode process. This is a message, right? Encrypted. Is it encrypted or encoded message? So they can get something readable. So you can see this whole process of encode and decode, and it's also applicable in the speech synthesis domain. First, what you have to do in the speech recognition or the model learning stage, what you have to do is to encode the speech signal into some compressed signal or some tokens, whatever tokens it is. But once you get those tokens, suppose you want to have speech again, then you have to go through this process of decode. Are you with me? You have to come through with this process of a decode, which is going from the tokens of speech or the high level information or the latent semantics of the speech. You go from there and you do the decoding, then this time you got speech. And in speech, we don't call the decoder, we call it vocoder. And I think that the VO means voice and the coder means the decoder or something like this. But you may ask, so suppose you do speech recognition, what do you call the encoder? So say you turn the speech into some tokens, actually text, right? Indeed, people do not call it some special term. People just call that speech recognizer. This is just for some 101 on the vocoder. And HiFi-GAN is a typical or falls into the category of a vocoder. So the input of the vocoder is usually mel-spectrogram. I don't want to write it. Let's go to the, directly go to the, yes. As you see, this is a vocoder. This is a HiFi-GAN, but any vocoder would have the same architecture except the content would be something different than the stuff presented in the HiFi-GAN paper, okay? The input is mel-spectrogram. Actually, should be called mel-scaled spectrogram. For those of you who do not know what is spectrogram, you first have to know what is spectrum. Okay, then a spectrogram means that you run short. A spectrum is obtained by doing Fourier transform on a speech signal, right? But suppose you have speech signal again, but you do something called a short time Fourier transform on the framed speech. What do I mean by framed? Instead of the speech signal here is the whole signal, or the whole utterance, the whole recording, and what I mean by framed is you chopped the speech signal into overlapped segments, and for each tiny small segment, which is about 20 to 30 milliseconds, you run Fourier transform on it, and people call that short time Fourier transform. And so you can definitely imagine that this is something I call the T times K. I mean, maybe K is the size of the frame, okay? The T means the number of the frames. And after short time Fourier transform, the T does not change, right? And the row columns start to become the number of FFT, right? So, or F Fourier transform. Usually it's half, but it's trivial. Then you can see in the spectrogram, it looks very much likely the image. So you can see the intensity of certain area, a certain frequency at a certain time point is higher than the other ones. This is called spectrogram. But if you run the Fourier transform, before you run the Fourier transform, after the Fourier transform, you pass this through a mel-scaled filter bank. It's called filter bank. You have lots of filters. So instead of having number of FFT size, then suppose the number of your filter bank is L, and then you compress this spectrogram actually into a size of L times T. And what do I do? So you run this filter, especially this filter, on the spectrum of at time T, then you got a point here, right? And then you run the second filter on the spectrum on time time equal to 1, then you got another value here. And you keep doing this, you got all the values at T equals to 1. And you do the same thing unless you fill everything in this. And this is how you obtain mel-scale. I prefer to mel-scaled spectrogram. Okay. So this is the fundamentals of the vocoder, and let's see what did these authors do, or what's the new thing they've done. So it all started from 2016 when everything started from the 2016. The paradigm of text to speech shifted because before that, people were still using something called the generative model. It's not this generative model we're talking about today. It's about, suppose I give you text and I want you to estimate what's the probability of the speech given the text, okay? Before that, before 2016, I think the main framework was to estimate a certain type of a token. How do you say that? Signal, okay. So indeed, they're trying to estimate this probability. What does that mean? It means that I want to say, okay, suppose I have a phoneme A. What's the distribution of the signal given? Suppose the underlying text is A. This turns out to be extremely difficult to estimate, and it has this is why it's called a generative model, okay? But nowadays, people do not care that much. They just try, when you ask this question, and they start to train. They use the Bayesian rule. You can do the math by yourself. All they have to know is to this, right? If you apply the Bayesian rule, it converts this question to this one, and to estimate this one, they leverage something called a discriminative model, which does not care about the distribution of, for example, this time it would be sorry, this should be speech. And if you break down this, you would definitely get something like this, right? So this is the way that people convert the generative model into the problem of a discriminative model. So you don't have to get a distribution of this p token given signal. All you have to do is just run neural networks on top of the signal. Then once you get the estimated token from the network, you only need to compute the cross-entropy loss, for example. You can have more sophisticated loss, but the cross-entropy loss is the most simple one. All you have to do to compare whether the estimated token is the same or has the probability of 1 as the transcribed token, okay? Makes sense? So this is what the WaveNet does. But the issue of WaveNet is it's very slow. Why? Because it uses a autoregressive structure. So to estimate the probability of the token, you not only have to have the current signal, but you have to have all the history. Let me use another color. You have to have the history. All history matters to estimate the next token. Oh, sorry. Yeah, next token. Actually, in this case, the token is the wave signal value. So this makes the training very, very slow. And given the history, it's all autoregressive. Think about this. Suppose you want to synthesize 5 seconds of audio. And the sampling rate, suppose this is 22 kilohertz. That means you have to synthesize about 100K samples, and each sample is dependent on the history. The samples are synthesized one after another one. So this makes the synthesizer process very slow. And the people do come up with something new. For example, it's the same author. They come up with a parallel wavenet. They use the flow model. Okay. Yeah, flow. I would definitely give you another tutorial on what is a flow model or how it's being used in the speech synthesis. I guess glow, right? Yeah, I think I would definitely just have another video on this. You can search this. Probably at the time you watched my video, I already made a tutorial on this. Just search this at OLED Wave YouTube. Okay, but today I'm not gonna go into it. But having this type of thing makes this faster, but it's still fairly slow because the model, the basis model is autoregressive. And then people come up with the generative adversarial networks, GAN. So when you have a GAN model, this can be way faster. Why? Because you don't have to have the autoregressive framework anymore. So all you have to do is to get the spectrogram of the whole utterance and pass through that through some CNN and compare the generative audio, then send it to the discriminator and see how that compares, right? So the autoregressive is not necessary. But the issue of the GAN model is the performance or the quality of the synthesized speech is not very satisfactory. Especially the, I think maybe some of you have heard of the mel-GAN. It's very easy to understand and easy to implement and maybe easy to train, but the quality is way, way behind the autoregressive method, which is a wavenet or something else. Definitely people start to improve on this, but not much progress until these researchers come up with the HiFi-GAN, which is still GAN, but they have shown that this has a way better quality than mel-GAN, and they say this is even better than wavenet, but the inference speed is way faster. It seemed like a free lunch to everybody, but how does it work? Let's see. Okay, let me remove this. I think this is their architecture. I think the model architecture. Like we just mentioned, this is the vocoder, but this part is easy to understand. There are this amount of KU. What does that mean? How to say this? I think they call the KU times. And I think that means you stack the convolutional layers KU times. Okay, this is not just a one CNN block. This is just blocks are stacked together, and this is why you see the number of channels start to decreasing once it's starting to reach the raw waveform. That makes sense, right? So because once you get to the raw waveform, what's the size of the channel? 1, right? Because audio, unless you want double channel, I don't think people do 2-channel synthesis, single channel. But the mel-spectrogram, what's the size of the channel? Right. the FFT size, or sorry, it's not FFT size. It's the size of the male filter bank, or the number of the filters in the male filter bank. Okay. I know lots of people are sometimes. I think I might have made a small mistake in the previous the explanation in the beginning. The mel-spectrogram is not done through passing spectrogram through a filter bank. It's by stretching the frequency according to the mel scale. So it's still a spectrogram. So the number channel in the mel-spectrogram is still the size of the FFT. Actually, it's divided by 2. So I hope this can rectify the errors I made in the beginning. But it's trivial. It doesn't affect you to understand this whole thing. And this is the key part. MRF is called the multi-receptive fields. I suspect that this is something that this also borrowed from computer vision, because I think receptive field is a common term in computer vision. But I'm not a computer vision guy, so I'm just trying to explain how this model works literally. Okay, you can see this is why it's called multiple. They have KR blocks. Okay, you can see this is why just the MRF part, they have 1, 2, 3, 4 in this case blocks, and for each block it will synthesize one waveform, I think, and yeah, one waveform, and the different waveforms are gonna be summed up together to have the final raw waveform. And in each block, it's called a rest block because it has this ResNet connection, right? And the leaky ReLU is easy to understand. It's just the activation function, nothing fancy here. The only thing fancy here is the dilation. So you can see my understanding of this is this creates the stuff they talk about here. It's called a multiple period discriminator. This is definitely new. It's called multiple period discriminator. How to say this? And you can see at each layer, okay, at each layer, they have this type of convolutional module output with different dilations, which is shown here, or it's not shown here. It's can be later on be used from here. Remember, they're training a model called GAN. Let's see this. Remember, they're training a model called GAN. When you have a GAN, you definitely, what we just talked about was generator. After you generate stuff, you want to use a discriminator to tell whether this is true or false, or real or fake. And you can see this. This is their newly proposed multiple period discriminator. And you can see they're saying that I can reorganize the speech samples or reshaped from 1 dimension to 2 dimension. But I can definitely have almost infinite number of reshaping, because I can definitely choose the period, right? I can, in this case, I think the period equals to 3, right? Then you can reorganize this waveform. Then you pass that through your, actually, it's also a stack of CNs. You get a real or fake. But you can definitely have a period of 5, period of 7. And the reason why they're choosing those prime numbers, actually, they start from p equals to 2, was because suppose you choose p equals to 2 and p equal to 4, and then you would definitely see that you have overlapping between these two reshaping results, right? The reason they use these prime numbers, they're trying to reduce the overlap so they can make the discriminators to be separated from each other, so they can provide maximum discriminability. Sense. And then after we understand this, we can come up back to take a look of the dilation here. You see, the whole point of doing dilations on the different blocks with different dilations was to generate having multiple generators. To generate audios with different dilations, so that later on they can pass those audios generated with different dilations through the MPD of the different multiple predictor, multiple period discriminators. Okay. And let's look at the loss. The GAN loss is very easy to understand. I don't think I need to explain this. This is standard GAN loss. The mel-spectrogram loss, this is the generation loss. Okay, this is just a generation. Suppose you go from underlying tokens or text tokens or some word piece things, semantic things to the speech. You can always have the generated speech and get the mel spectrogram of it, and then compare that with the spectrogram of the original speech. You have the ground truth, right? And remember, this is L1 norm. This is easier to understand. And here, the feature matching loss is how the MPD kick in. Okay, the AI denotes the ith layer of the discriminator. Okay, ith layer of the discriminator. So my understanding, or I think the author meant, this whole thing, they have many layers. So different layers will generate intermediate features with different dilation ratio, right? And you can definitely compare the feature generated using discriminator. So discriminator is not let's rewind this back here. It's not this, it's this. So the MPD, they have many layers. So this is layer 1, this is layer 2, this is layer 3, 4. And the different layers, you have intermediate outputs. They call the ICE features. Okay, the for example, second layer, the second layer's feature, and you use that. First of all, you generate using the generated speech to get the feature. Okay, then you use the original speech or the ground truth speech to get the feature at the ICE layer. Okay, and they compare the L1 norm, or you get the L1 norm. And then this is Ni means the number of features. I think this is trivial. It's the number of features. And you may ask, how do you kick in the multiple period discriminator? It's here. In this case, there's no multiple period. This is a single period or single thing, okay? But once you see this equation here, this, once you add the summation or introduce the multiple period discriminator, so you have to go from 1 to k. So you can see that when you compare the generative loss and the discriminator loss, you have to do with the k discriminator and the k generators. Does that make sense? And the same thing, you have to not only the adversarial loss, but also the feature map matching loss. But for the mel loss, I don't think, or it also doesn't mean that you would have this discriminator, because the mel loss is just the mel from speech to mel-spectrogram. That you don't have to have a discriminator or generator. So you don't have to have a discriminator. You have a generator. Makes sense. Experiment. I think the experiment is fairly easy to understand. Let's quickly look at the result. WaveNet. This is better than WaveNet in terms of mouse score, but this is a way faster than WaveNet. See? This is about 167.86 faster, I think. Or is this RTF? I think it's trivial. It's all you have to remember is way faster than WaveNet, and it's the performance or the quality of the speech is much better than mel-GAN. You can see the mel-GAN is slightly faster than the GAN, the HiFi-GAN. And the V3 is probably they're talking about they squeeze the model. They can get very fast, but they suffer a little bit from the quality of the speech. They've done an updation study. They have tried to play something called a multi-scale discriminator. S means scale. This is not new, because this has been used in mel-GAN before. How does that work? It's like this. It's just try to get the long-term dependency and the context window, right? On the temporal scale. It's very easy to understand, right? You see this, but you can definitely choose different temporal scale to have a different multiple scale discriminator. Make sense? This is not new in the paper, because this has been proposed in the mel-GAN before. And they're saying that because mel-GAN doesn't have the MPD, so they added the MPD on top of mel-GAN, and you see this helped the mel-GAN a lot. They're saying that the MPD is very important, because once you take out MPD, the quality of the speech dropped significantly from 4 point something to 2 point something. But if you just remove the multi-scale discriminator, it only dropped 0.5 or 0.4, which is dropped way less than something that when you do not have the MPD. They also compared on the VCTK to see that whether when they met a unseen speaker, how the thing work. And the conclusion is roughly, or it's also consistent with the conclusion they got from the single speaker. Okay. And also they have shown the pixel-wise difference in the mel-spectrogram domain. I personally cannot see too much from this. All right. Let me know if you have any questions. Comment in the comment section. If you like our channel and our video, please hit subscribe and share that with your friend. And that's it for today. Goodbye.